Hello friends, here we have yet another interesting question. We need to find the equation of the tangent plane at the point 1, 0, 0 by finding the derivative with respect to x and y for z. We have been given the equation as follows, and we notice that this equation is cyclic in x, y and z. That is, if we substitute x by y by z and z by x, then we get the same equation in a rearranged form again. You also may notice that the partial derivatives of z with respect to x and y are arbitrary. So we may also find the partial derivative of y with respect to x and z, or similarly for x, and arrive at the same result. Now we have also, when if we find the we need to find in order to compute the values of partial derivative of z with respect to x and y. Hence we have and then by cyclicity we can figure out the same for the partial derivative with respect to y and the partial derivative with respect to z. Here we have, for the partial derivative with respect to x, we first take the partial derivative of e raised to xyz with respect to x, and that is yz e raised to xyz. So how do we get it? We have e raised to xyz. In normal differentiation, what we do is, in total differentiation, when we have d by dx ax square, for example, and we assume that a is a constant, or a is invariant with respect to x. As x changes, a does not change, so we take out a and find the derivative of the function inside, and that gives us, in this case. Similarly here, we first find the derivative of e raised to xyz with respect to xyz, and then the partial derivative of xyz with respect to x, and that is equal to yz. Next we have ln x square plus y square plus z square. Similarly, we get here 2x by x square plus y square plus z square. Since we first take the derivative with respect to x square plus y square plus z square, that is 1 by the value, and then we take the derivative with partial derivative with respect to x. So x square gives us 2x, and these two give us 0, as we suppose they are invariant with respect to x. So while finding the partial derivative with respect to x, we hold y and z as constants. For the part sin xy plus yz plus zx, we have cos xy plus yz plus zx, and then the partial derivative of this part with respect to x, and that gives us y plus z. So here we may write the general form for f of x as yz e raised to xyz plus 2x by x square plus y square plus z square plus y plus z cos xy plus yz plus zx. Here since we have been given the values xyz as 1, 0, 0, we may substitute them here. So this cancels out to be 0, this again cancels out to be 0, and we get these cancel out to be 0, so we get 2 by x, which is equal to 2. Now in order to find fy, we may substitute x, y and z by y, z and x in this whole equation, or we may change these variables to 0, 1, 0, since this was with respect to x, so we had x equals 1, and then now since we calculate with respect to y, we take y equals to 1, and then again we substitute in the same equation. So this again gives us 1, but since z is 0, like this part gives us 1, since z is 0, this equates to 0 again, and this will equate to 0 again in f of z as well, so for f of z as well, so we can remove this part entirely. Now for this part, in this case we have x equals 0, so this equates to 0. For this part we have y plus z, which is equal to 1, and cos of this part, which again equates 0. So since whenever two variables from x, y and z are multiplied, you may notice that then that part shall yield 0, because we have a combination which has 0, 1, and two combinations which have 0 and 1, and one combination which has two zeros. So this part will equate cos 0, which is equal to 1 in all cases. This part will equate 0 in all cases. And for this part, we have for fy, we have this, and for fz, we have 0, 0, 1. So when we substitute y equals 1 and z equals 1, these two parts yield the same result, and this also yields the same result. So we have 2x by x squared plus y squared plus z squared equals to 0 for both of them, and this part equates 1 for both of them. Then we may write this as fx equals to fy equals 1 and fz equals 1 again. Now in order to find the partial derivatives, we have the formula. For example, for this part we have and with the partial derivative of z with respect to y, we have minus fy by fz. This we can equate by substituting the values. We have minus 2 and minus 1 here. Now in order to find the plane, the 3D plane that we are asked for at the point 1, 0, 0, so we have by till now we have so these two values give us the change that is caused in z by x and y respectively when we hold the other one as invariant. So when we calculate the partial derivative of z with respect to y, we hold x as invariant and measure the change caused in z due to changes in x. Now here, in order to find the equation of tangent plane, as we have in, for example, a two-dimensional plane, we have delta y equals m delta x, or delta y by delta x equals m. In a three-dimensional plane, however, since we are finding with the changes in the z direction, we have delta z equals delta x partial derivative of z with respect to x plus delta y into partial derivative of z with respect to y. Now we can substitute these values as minus 2 and minus 1, and that gives us delta z equals to minus 2 delta x minus delta y. Now, since, as we do in a two-dimensional plane, we have delta z equals z minus z naught, delta x equals x minus x naught, and delta y equals y minus y naught. Since we have been given these values, we have delta z equals z minus 0 equals z, delta x equals x minus 1, and delta y equals y minus 0, which is y. So we have z equals minus 2, x minus 1 minus y, and that gives us z equals minus 2x minus 2 minus y, or we may plus 2 minus y, or we may rearrange it as 2x plus y plus z equals 2. So we get this as the tangent equation of the tangent plane at this point. For other interesting courses related to computational math, you may refer the links below.